Hello everyone. Today we are going to analyze this simply supported beam. In this beam we have uniformly varying load. It varies from 0 in the left end to W in the right end. To find RA, let us take a moment about B. In this case we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. RA is acting in the clockwise direction, so it will be positive, and the distance is L, so RA into L. The UVL is acting in the anti-clockwise direction, so it will be negative. For the UVL, we have to multiply the area with the centroid distance. This loading is in the shape of a triangle. We know the area formula of a triangle, half into BH. Here the breadth is L and the height is W. So this is the area. The centroid distance about the height is 1 upon 3 into breadth. Here the breadth is L. So it is 1 upon 3 into L. For RA, we will get WL upon 6. To find RB, let us take a moment about A. In this case, we have to follow left hand side rule. RB is acting in the anti-clockwise direction, so it will be positive and the distance is L, so RB into L. The UVL is acting in the anti-clockwise direction, so it will be negative. We know that for the UVL we have to multiply the area with the centroid distance. We know that this is the area. The centroid distance about this point is 2 upon 3 into breadth. Here the breadth is L, so it is 2 upon 3 into L. For RB, we will get WL upon 3. Alternatively, we can find RB using this rule. RA and RB are acting upwards, so both of them are positive. The UVL is acting downwards, so it will be negative. For the UVL, the total load is the area. We know that this is the area. After simplifying for RB, we will get WL upon 3. Using the right hand side rule, we can find the shear force values at just left of A and at just right of A. At just left of A, the shear force will be 0, and at just right of A, we have RA. It is acting upwards, so it will be positive. To find the shear force at just right of B and at just left of B, we can use left hand side rule. At just right of B, the shear force will be 0, and at just left of B will be RB. It is acting upwards, so it will be negative. We found the expressions for the shear force on both of the ends. To make the expression to find the shear force at any point of the beam, let us make a section at a distance of x from the point A. We need to find this height. For the distance of L, the height is W. So for L, it is W. But we need the height at a distance of x. So we have to multiply with the x. In this way, for this height, we will get Wx upon L. Using the right hand side rule, let us find the shear force in the section. RA is acting upwards, so it will be positive. The UVL is acting downwards, so it will be negative. For the UVL, we have to take the area of this triangle. We know the area formula of a triangle, half into BH. Here the breadth is x and the height is Wx upon L. Using this expression, we can find the shear force at any point of the beam. Let us find the bending moment in this section using the right hand side rule. RA is acting in the clockwise direction, so it will be positive and the distance is x. The UVL is acting in the anti-clockwise direction, so it will be negative. We know that for the UVL, we have to multiply the area with the centroid distance. This is the area of this triangle. And the centroid distance about the height is 1 upon 3 into breadth. Here the breadth is x, so it is 1 upon 3 into x. Using this expression, we can find the moment at any point of this beam. Here you can see the shear force diagram. This is a parabolic curve. In this point, the shear force becomes 0. In this point, there will be maximum bending moment. We can make a section in this point and find the distance. You can see that I have made a section in that point. For the shear force at any section, just before we have made this expression, we know that in this section the shear force is 0. So we can equate this to 0. After simplifying for x, we will get L upon root 3. Now let us find the maximum positive bending moment. Just before we have made the expression for the moment at any point. In that, instead of x, we have to apply L upon root 3. X cube will be L upon root 3, the whole power cube. We can write that L upon root 3 into L upon root 3, the whole square. So we will get L upon root 3 into L square upon 3. We can eliminate this L. 6 into 3, it will be 18. We can take WL square upon 6 root 3 outside. And for these two terms, we can take LCM. We can eliminate 2. Here it will be 3. 3 into 3, it will be 9. So this is the expression for the maximum positive bending moment. We have found the expression for the maximum positive bending moment. And we know that in the simply supported ends, the moment will be 0. Here you can see the bending moment diagram. This is a cubic curve. Using the Macaulay's method, we are going to find the expressions for deflection and slope. For that, we have to make a section. You can see that I have made a section XX at a distance of x from the point A. We need to find the moment in this section that we have done already. We just have to copy that. We have to equate the moment to EI d square y upon dx square. From these two terms, we can take W upon 6 outside. We have to integrate with respect to x on both of the sides. When we integrate this, we will get this. To integrate x and x cube, we can use this formula. For x, it will be x square upon 2. For x power 3, it will be x power 4 upon 4. C1 is the constant. One more time, we have to integrate on both of the sides. When we integrate this, we will get y. When we integrate x square, it will be x cube upon 3. When we integrate x power 4, it will be x power 5 upon 5. Here there is no x, so we have to multiply with the x. C2 is the new constant. 2 into 3, it is 6. 4 into 5, it is 20. In the point A, there is a vertical support. If there is vertical support, there will be no deflection. So when x is 0, the deflection y will be 0. In this, we need to apply both of them. This term will be 0, this one will be 0, this one and this one will be 0. So for C2, we will get 0. In the point B also, there is a vertical support. So when x is L, the deflection y will be 0. In this one, we have to apply these. And for C2, we have to apply 0. Using a calculator, we can add these two terms. When we add, we will get this. Then we can eliminate L. Here it will be cube. For C1, we will get this. Let us take the slope equation. In the slope equation, let us apply C1. From these two terms, we can take a W upon 6 outside. Then from these three terms, we can take a 2 outside. 6 into 2, it will be 12. Let us keep this equation as number 1. Using this equation, we can find the slope at any point of the beam. To find the slope in the left end, in this equation, instead of x, we have to apply 0, so that we will get theta A. To find the slope in the right end, that is in the point B, in this equation, instead of x, we have to apply L, so that we will get this. We have to find the location where there is maximum deflection. Slope will be 0 in the point where there is maximum deflection. So for this, we need to apply 0. We can take this term on the other side. It will be 12 EI upon W. When we multiply anything with a 0, we will get a 0. Let us change the sign of these three terms so that we will get this. Let us keep x as NL. Instead of x, we have to apply NL. We can eliminate L and here it will be cube. L into L square, it will be L cube. We can take L cube outside and take it on the other side. 0 into 1 upon L cube, it will be 0. For these three terms, let us take LCM. Let us keep 30 as LCM. Finally, we will get this equation. Let us keep m as n square so that we will get this equation. Using a calculator, we can solve this equation, or using this formula, we can solve it. We know that m is n square. So instead of m, we can apply n square. For n, we will get two values. But this one is not applicable because it is more than 1. So we have to proceed with this value. We know that x is NL. So x will be 0.5193 L. Now let us take the deflection equation. In that, let us apply C1 and C2 so that we will get this equation. From these two terms, we can take W upon 6 outside and we can take EI on the other side. It will come in the denominator. Then from these 3 terms, we can take a 2 outside. 6 into 2, it will be 12. For these 3 terms, we can take LCM. Let us keep 30L as LCM. 30 into 12, it will be 360. This is the expression for the deflection. Using this, we can find the deflection at any point. To find the deflection in the center, in this, instead of x, we have to apply L upon 2. After simplifying, we will get this. We will get a negative expression. That means the deflection occurs downwards. We can keep the expression in decimal also. Now we are going to find the maximum deflection. Just before we found the location where it occurs. In this one, instead of x, we have to apply this. Finally, for the maximum deflection, we will get this. Here you can see the elastic curve. Now we are going to end this session. Thank you for watching this video.